So in this video, we're going to look at the first section of the organic chemistry topic. Organic chemistry is all about the study of a type of chemical compound known as an organic compound. Now, there are lots of different types of organic compounds, but the one thing they have in common is that they all generally contain large amounts of carbon and hydrogen. So in this topic, we will look at different types of organic compounds you can have, but the starting point is to look at where organic compounds actually come from, and the main source of them is a substance known as crude oil. Crude oil is a useful substance that's dug up from underground, and the reason it's useful is that it contains lots of organic compounds. The proper way to describe crude oil is as a mixture containing many alkane hydrocarbons. Alkane hydrocarbons, as we'll look at in the next section, are just one type of organic compound and a very useful one. Crude oil is also a finite resource. Finite just means the opposite of infinite. In other words, it's non-renewable and will run out eventually. It's a very valuable resource because it's known as a feedstock for the petrochemical industry. The petrochemical industry is basically the industry that makes things like plastics and different materials and different chemicals and medicines, and crude oil is a very useful resource for them to use. Now, the crude oil that you take out from underground isn't actually particularly useful by itself. It's a whole big mixture of different compounds, and to make it more useful, we have to get the mixture of compounds separated out. The technique we use to separate crude oil into useful compounds is known as fractional distillation. The special name we give to the groups of compounds that we separate crude oil into is fractions. So a fraction just means part of the whole. So we're taking all the crude oil and splitting up into different sections or different amounts known as fractions. Now, how fractional distillation works is that you take the crude oil from underground and you heat it until it's all turned into gas. The gas crude oil then enters a container known as a fractionating column. The job of the fractionating column is to split up the different compounds in crude oil into separate containers. The fractionating column basically is a big box that contains lots of different layers, and gases can travel through these layers by travelling through these little kind of bubble caps here. And each layer represents a point in the column where a separate layer of the mixture can gather. The key characteristic of the fractionating column is it has a heat gradient. It's very hot at the bottom and very cold at the top. That allows you to separate out different compounds based on their boiling points. For substances that have got high boiling points, as they move their way up through the column, they will cool down beyond the point past their boiling point. Once you cool down below your boiling point, you turn back into a liquid and you'll gather in one of the layers of the fractionating column. For substances that have a very low boiling point, they have to get quite cold before they turn back into liquid, so they will turn back into liquid more towards the top of the column. So the end result is that all the different compounds you've got in crude oil will separate out into separate layers of this column depending on how cold they have to get before they turn back into liquid. Now, in terms of what you have to know about the result of the fractionating column, you need to know the names of a few different fractions or a few different layers of the column and one use for each of those fractions. So going from the top, we have refinery gases, then petrol, then naphtha, then kerosene, then diesel, then fuel oil, then bitumen. For the uses of these different fractions, refinery gases are used for bottled gases, for example for a barbecue. Petrol is a car fuel. Naphtha is used to make chemicals and plastics. Kerosene is used as aircraft fuel. Diesel is used as car or train fuel. Fuel oil is used for ship fuel, and bitumen is used for road surfacing. Now, what you might find after doing fractional distillation is that you have too much of one fraction and not enough of another fraction. It is possible to convert one fraction or one of your layers into a different layer by carrying out a process known as cracking. The definition for that is the breakdown of larger unsaturated hydrocarbons into smaller, more useful ones, some of which are unsaturated. We'll cover what we mean by the words saturated and unsaturated later on in this topic. So now we look at the different types of organic compound you can obtain from this fractional distillation process. Now, one word we come across already, which I'm going to explain now, is hydrocarbon. Lots of organic compounds happen to be known as hydrocarbons, and they've got their own particular definition. A hydrocarbon is a molecule that consists of carbon and hydrogen atoms only. In other words, it can't contain any other different atoms. Now, hydrocarbon is one way of describing organic compounds. A slightly more general way to describe organic compounds is to categorize them into different groups, and those groups in this topic are known as homologous series. And homologous series just describes the different families or groups that you can put organic compounds into to make them easier to keep track of. Now, if you're going to say that two compounds are found within the same family, known as homologous series, they have to have 4 characteristics in common. So it's quite a long definition here. They need to have the same general formula, we'll cover that in a second. Similar chemical properties, so they should behave and do similar chemical reactions as each other. They should have a gradation in their physical properties. That basically means as you go down the family, the boiling points and melting points should gradually increase. And the last one is that they should differ by a CH2 unit, which means as you go down the family, you add on a carbon and 2 hydrogens to every molecule in the family. Now, it's easier to understand what's meant by homologous series if we actually look at a couple of homologous series or families. In this video, we're going to look at the first two, which are the alkane family and the alkene family. The alkanes are the most basic type of organic compound. They're quite unreactive and they have no functional group, which would make them reactive. You need to know about the first 4 members of the alkane family, and the way they're categorized is by the number of carbons they have in them. The first member has 1 carbon, the second member has 2 carbons, third has 3, and fourth has 4. Now, when you're drawing organic compounds, the thing to remember is that carbon always has to have 4 bonds. So your starting point is to work out the number of carbon atoms you've got, as I've drawn down here, 1, 2, 3, or 4. The remaining bonds in the alkanes, because there's nothing interesting like a functional group, as we'll see in later on homologous series, for these basic ones, you're just going to make up the remaining bonds by using hydrogen atoms. So for the first one, you draw in 4 hydrogen bonds. For the second one, each carbon gets 3 hydrogen bonds, and so on, making sure that every carbon has to get 4 bonds in total. We can give formulas for these compounds just by counting up the number of carbons and hydrogens contained. And what we can notice with the formulas as we go a pattern, as you go down each member of the family, you increase the number of carbons by 1, and you increase the number of hydrogens by 2. Your starting point is CH4, and putting that into like an algebra kind of format, we come up with this as a general formula. CnH2n plus 2, when n means the number of carbons you've got in your particular molecule. The fact that it's H2n plus 2 just comes about because the first one doesn't have 2 hydrogens, it's got 4 hydrogens, so you always have to add 2 to your total. The final thing we need to know about these structures is what you would call them, and we need to introduce the system we use to name organic compounds. Organic compounds basically get a first name and a second name squeezed together. The second name comes from the family you find them in, so in this case we're in the alkanes, so the name at the end of their name is always going to be ANE for ane. The start of the name comes from the number of carbons you've got, so either 1, 2, 3 or 4, and we have a special term to describe the number of carbons. If you've got 1 carbon in the compound, it starts with meth, 2, eth, 3, prop, and 4, bute. So putting those 2 things together, we will end up with the following names. The first one is methane, second one ethane, third one propane, and fourth one butane. Now, we've already said that the alkanes are pretty unreactive, but they do one chemical reaction quite well, and that is combustion. Now, in everyday terms we refer to combustion as burning something, but it has got a proper definition, and that is a reaction in which a fuel reacts with oxygen, producing oxides and releasing heat. And the alkane molecules are pretty good at doing combustion reactions. Now, there are actually 2 different types of combustion reaction depending on how much oxygen you've got. The main type of combustion is known as complete combustion, and that would take place when you've got lots of oxygen in your reaction. The general equation for the reaction of an alkane with oxygen in complete combustion is that the alkane plus oxygen will make carbon dioxide plus water. You could be asked to give the symbol equation for the complete combustion of any of the alkanes above. So for example, if we had methane, you would have CH4 plus O2 goes to CO2 plus H2O. Obviously this equation needs balance as well. The easiest way to balance these combustion equations is to balance the carbons first. So we look at the carbons on the left, we've got 1 on the left, 1 on the right, that's already balanced. Then we look at the hydrogens, we see there's 4 on the left and only 2 on the right, therefore we need to put a 2 in front of the H2O. And then if we look at the oxygens, we've got 4 oxygens on the right but only 2 on the left, therefore we need to put a 2 in front of the O2 to give us a balanced equation. A slightly different type of combustion that can take place is when you're trying to burn an alkane in a small amount of oxygen. The equation changes slightly. Instead of making carbon dioxide plus water, you actually make carbon monoxide plus water. So if we see an example equation, let's say we're given an equation for the incomplete combustion of ethane, C2H6. Instead of writing CO2, we're obviously going to write CO for carbon monoxide this time. We balance it in the same way. We tried to balance the carbons first, so I needed 2 in front of the CO on the right hand side. We balanced the hydrogens next. We got 6 hydrogens on the left, we need 6 on the right, so it's a big 3 in front of the H2O. And then the oxygen's a little bit tricky here, because on the right hand side we've actually got 5 oxygens, so we need to get 5 on the left, but O2 only goes up in batches of 2. What you're allowed to do here is actually use a fraction or a decimal to give the correct number of oxygens. So what I would do here is, I would say we're going to have 2.5 O2s. 2.5 times by 2 is just 5. So 2.5 O2s is just 5 oxygen atoms, which balances out the oxygens on the right hand side as well. Now if you were doing combustion reactions, you might want to prove that you've actually made carbon dioxide plus water, assuming it is complete combustion. So there's a couple of chemical tests we need to prove those two compounds. The test for carbon dioxide is to bubble the gas through lime water, and you'll see it turn from colourless to cloudy. And the test for water is that it will turn anhydrous copper sulfate powder from white to blue. Now there are a few negative impacts of the combustion of alkanes you need to know about. The first is that combustion produces carbon dioxide, which contributes to the greenhouse effect. Incomplete combustion produces toxic carbon monoxide and soot. And finally, the sulfur impurities that you can naturally find within alkane fuel can often lead to the formation of acid rain. The next family we'll look at in this video is the alkene family, which is very similar to the alkane family. Now the alkenes, like the alkanes, are hydrocarbons. They contain only hydrogen and carbon. But they are more reactive than alkenes. The reason they're more reactive is that they contain within their structure something known as a functional group. In terms of what a functional group actually is, a functional group is just the term given to a reactive group within an organic molecule. And the reactive group within the alkene molecule is a carbon-carbon double bond. Now because alkenes have got carbon-carbon double bonds, they actually get another term associated with them, which is unsaturated. If you're unsaturated, you don't contain as much hydrogen as you possibly can because some space is taken up by a double bond. So an unsaturated molecule, like alkenes, contain one or more carbon-carbon double bonds. Like the alkanes, we need to know the names and structures of the first 4 alkene molecules. Now to be an alkene, you obviously have to have a carbon-carbon double bond, so the first alkene doesn't have 1 carbon, because you couldn't get a double bond to another carbon if there's only 1. We start with 2, and then we work our way up. So we have 1 alkene which has got 2 carbons, 1 alkene which has got 3 carbons but only 1 double bond, and then 2 more alkenes which have got 1 double bond and 4 carbons. But you can see here that the double bond's actually in different positions, and one that's on the end and one that's in the middle. Now just like we did for the alkenes, we need to put in hydrogens so that every carbon gets up to 4 bonds. So at the minute they have a mix of 1 or 2 bonds, or 3, and we need to add the appropriate number of hydrogens so they all end up with just 4, as you can see here. Again, like the alkanes, we can give the formulas of those compounds by counting up the numbers of C's and H's. C2H4, C3H6 and C4H8 twice. From that we can get a pattern for a general formula for the alkenes. Generally you're going to double the number of carbons to work out the number of hydrogens. So the general formula becomes CnH2n. The naming of the alkenes is similar to the naming of the alkanes. They have a surname, which is ENE for alkene. And again, we give the first part of the name from the number of carbons in the compound. So eth is 2, prop is 3, and but is 4. So we can see ethene and propene for the first 2. Now you see for the 4 carbon alkenes, we've got 2 different names, but1ene and but2ene. The number here is used to distinguish these 2 very similar molecules because of the same number of carbons and hydrogens. The number represents the carbon atom, which contains the double bond. In this molecule, the carbon atoms 1 and 2 have a double bond, so we give the lower number 1. And in this molecule, carbons 2 and 3 have got the double bond, so we only give the lower number, we give carbon 2. That gives us but1ene and but2ene as their names. Now, alkenes are a little bit more reactive than the alkenes, so we need to know a few reactions that alkenes can carry out. The first one is combustion, And that takes place just exactly like the alkanes do combustion. If it's complete, you'll make carbon dioxide plus water. If it's incomplete, you'll make carbon monoxide plus water. The next type of reaction is known as an addition reaction, of which there's two examples. The first one is a reaction of an alkene with bromine. If we take an alkene, for example ethene, and react it with a molecule of bromine, an addition reaction takes place where the two molecules add together to form one product, which looks like this. So you can see here that the double bond has been broken, and in its place we've got two new bonds to bromine. Now that reaction is quite interesting because it can actually give you a test to prove you've got an alkene. Bromine naturally has got an orange colour when it's in solution, and if you were to do this reaction, because the bromine's used up, you'll actually see the test tube turn from orange to colourless as the bromine is reacted. So to test for an alkene, you would shake the alkene with bromine water and it would turn from orange to colourless. The second type of addition reaction is with steam, which is the gas form of water. So in this reaction again, the double bond in the alkene is going to break and we're going to form two new bonds. The two new bonds are formed to water, but it's not water as one thing. The water splits in two. It splits into an H and an OH, and those two parts are going to add to the alkene molecule. And that actually forms this type of molecule known as an alcohol. The final type of reaction for the alkene is known as a polymerization reaction. In a polymerization reaction, you're going to join lots of small alkene molecules together to make a really long chain. So in polymerization, it's a process of joining monomer molecules. Monomer just means like one molecule by itself. We join lots of them together, we form a really long chain called a polymer. So how that might work is we might take a monomer alkene, maybe for example ethene, and to show that we've got a large number of them, we normally put a small n beside them, where n means a large number. Now the large number of ethene molecules are going to join up to form a long chain. How they do that is they break their double bond between the two carbon atoms and use that leftover bond to form up links to the molecules either side of them. So we normally show that like this. We've broken the double bond and the two bonds dangling out either side of the ethene molecule, it's implying that they're joining up with another ethene either side of them. The little n in brackets implies we got the same number of links as we had the original ethene molecules. The name for this product comes from the fact it comes from ethene and we made a polymer of it. It's called polyethene. Sometimes it's known in everyday life as polyethene. A second type of polymer it's useful to know about is PVC, known as polyvinyl chloride. Polyvinyl chloride is made from vinyl chloride, which is an alkene a little bit like ethene, except instead of 4 H's, it's got 3 H's and 1 chlorine. So that molecule I've just drawn is known as vinyl chloride. And it joins up exactly the same way to form a long chain known as polyvinyl chloride, PVC.